Hello, everybody, and welcome. This is the next episode of our Prague seminar for mathematical physics. And I'm very happy I can introduce our today's speaker, Andrey Krutov, visible on the screen now. And he presumably prepared a very nice talk for us today. It will be about a group moment maps on linear homogeneous supermanifolds. So we are warned by this time, and it's your time. Thank you for coming.
For the kind of introduction, it's always a pleasure to speak here. Could you make it bigger?
Yeah, sorry.
So it will be some report on work in progress with analysis from Geneva. It's actually very nice, but it's somehow simple result. It's a couple of observations about different moment maps on exterior and symmetric algebras. Let me go to the outline of the talk. So we will discuss different moment maps. Which one will appear in our studies? So, of course, we will start with a classical moment map that is defined for some manifolds. So we have some invariant by vector, and then the moment map is, I will give a precise definition to remind you what it is. Then we will go to generalization of a Poisson manifolds to the quasi-Poisson manifolds when the Poisson directly doesn't satisfy the Jacobi identity anymore. And it will allow us to construct some moments but these values not in the algebra or dual of it, but in the corresponding integral group itself. And it was introduced by Alexey Malkin around 25 years ago. And then we also discussed some moment maps with values in the dual Poisson D group. So I will give precise definitions and interrelations between all of these moment maps during the talk. And we will be interested in very simple manifolds, mainly supermanifolds. So I want to speak about Poisson structures or some quasi-Poisson structures on symmetric and exterior algebras of some finite dimensional modules over my D algebra. So it's clear how to consider symmetric algebra as algebra of functions and manifolds. It's just polynomial functions. But if you want to treat also in the same manner exterior algebras, well, that's algebra of functions on the completely odd supermanifolds. And this all started with trying to understand different deformation of this exterior algebra of SL2. So the SL2 examples will be with us throughout all the talk. In the end, I will give some classification results for general simple Lie algebra and finite dimensional modules. But this was really a motivating example studying some simple algebras like a Clifford exterior algebra, corresponding Clifford algebra, and quantization of both of them. And later, I will give a light how it's to be connected by the Poisson story. And the last one, the quantized Clifford algebra, appeared in my talk, when was last time? 2 years ago here, approximately this time of the year. So it's a continuation of some old stories.
Andrey, could you make the slides bigger?
No. I think you should go out. No, maybe I should press F12 or something.
Yeah, I tried it already.
Another option is to save the file and open it via.
Yes.
Where is the plus?
Here.
Yeah.
Okay, maybe it's not.
You can try to save the file.
Or no, then it needs to be shared. So
Yeah, but then you can share the app.
yeah.
Maybe you can open it.
Okay, please. Sorry, I interrupted.
Okay. Right. So let's start our journey. So as I promised, the result is quite elementary in a way, but it will be a nice journey how we connect things together. So as I said, that my main tool will be supermanifolds, but very easy supermanifolds because some supermanifolds are associated to vector spaces that I then will create into super vector space. For super vector spaces, it's some Z2 graded vector space. And supermanifold. Go back. Yeah, and of course, morphisms in this category is Z2 degree preserving linear maps. And as a supermanifold, it's not in the 70s, in the 80s, and other people consist of a pair. The simplest definition, you have some underlying manifold plus some sheaf over this manifold that locally looks like, so you have some domain in your manifold, and locally your sheaf look like smooth function on this manifold, on this domain, tensors with some exterior algebra with n generators, and this n is a constant over all domains. So that's a nice definition. First example, what happens when I have a manifold associated with the superlinear space. Let me recall that you can consider the usual vector space as a very nice manifold. It's not the case in the supersetting, but you can associate some linear supermanifold to a supervector space in the following manner. So your underlying manifold is just even part of your supervector space, and the structure sheaf looks as follows. So this guy is just a function on your even part, tensor exterior algebra. In particular, we will consider very simple examples of such supermanifolds when we have either zero even part or zero odd part. So it will be either completely even, so mainly regular manifolds, or completely odd manifolds, and then our algebra function will be exterior, so we can treat these algebraic objects like geometry. Okay. And just a small remark that, again, I want to speak really about exterior and symmetric algebras, and the symmetric algebra could be considered as a polynomial functions. All right, now a bit of constructions. So I will start with a Lie group, possibly it's compact, and G will be corresponding to algebra, and in all examples it will be something like a simple or semi-simple, but the condition is really to have some non-invariant measure on G. Then for some finite-dimensional module that admit some non-degenerate invariant bilinear form, I will construct supermanifolds regarding if I have a symmetric or anti-symmetric form on my vector space. So if it's symmetric, then I cook from my module super vector space in the following manner. I put my even part to be completely zero, and my odd part will be isomorphic to my module. So the corresponding supermanifold will be a point with this sheaf of function on it. So it's C tensor some exterior algebra. As I promised, this is a supermanifold. So such modules I will call odd. And if my form is Q-symmetric, then I do vice versa. And this is just regular construction of the manifold corresponding to this. And in what follows, I will denote by F the polynomial function of the corresponding supermanifold, denoted by this QEV. So very simple setup is just help us to understand better about some structures on the exterior and symmetric algebras. Next slide, please. Example. Let's look at SL2. I will follow until the end of the lecture with the two examples. So just fix the generators. Let's look at the two-dimensional representation. So it's spanned by two vectors, weight 1, weight -1. Then we have a skew-symmetric form. So this module is even. And then our algebra of polynomial functions is just isomorphic to symmetric algebra of this. Another example is a joint representation. A joint representation is three-dimensional and admits symmetric linear form. So this module is odd. So we should hook, here is a form, and we should hook all the supermanifold from it, and then the algebra function is just its three-dimensional. It's very easy. Next, please. And in what follows, sometimes I will forget to put stars, but because we have this bilinear form on our model, we can identify these things. Now, let's recall definition of the classical moment maps. So we have, again, our Lie group, this the algebra. We have a non-degenerate bilinear form on G. And we can consider infinitesimal version of the action of our Lie algebra, given by these formulas that you know from the algebra standards. Then this manifold to hook Poisson to hook moments map. Of course, we need a bivector. So for bivector, by phi sharp, I will denote this map between forms and vector fields given by bivector. You just insert into a form as usual, just a bit of notation. And then, of course, a Hamiltonian G Poisson manifold is a triple when you have a manifold invariant bivector, which satisfies which Salton bracket vanishes, and the moment map that satisfies the following condition: the infinitesimal action of your vector fields could be hooked from your bivector and this moment map mu. You will see that all generalization will be in the same spirit. So they will allow you to hook infinitesimal version of the actions via some bivector, which will be not necessarily close. Let's see how it looks like in our very simple examples. So for our two-dimensional representations, let's speak about vector fields. So vector fields are derivations of our algebra of functions. Our algebra of function is this symmetric algebra. Again, I will always here consider some polynomial guides. And then derivation of this guide is just symmetric algebra itself tensor down. So we can define it on generators to an extent. Then, well, maybe a bit slower. So then the infinitesimal version of our action, of course, is given by this vector fields, which is easy to compute from the action. And we consider the Poisson structure given by bilinear form. So on generators of our algebra functions, we define it as just, sorry, it should be here instead of psi, but the Poisson bracket looks very easy. You take two generators and you compute bilinear form of x2. And then you extend it to be Poisson. Very easy. Then it's easy to calculate the corresponding Poisson B vector. It looks exactly what you expect. And the moment map could be derived explicitly from the condition for a moment map. So this is just example. Note that it lives here, so it's second degree in our algebra function standard on G star. So this is a guy here. Our second example of odd module. Now the picture is reversed, everything is odd. So algebra function is exterior algebra, then derivations look like this. Again, it's some kind of pre-commutative algebra, then you can identify derivation with this vector space. Of course, you can compute the corresponding infinitesimal action, which looks like here. And the vector corresponding to the Poisson structure defined in the same manner. Now your Poisson structure is on the super vector space. You do absolutely the same things. You just remember the parity. So you put -1 to the parity of objects when you move them. So it's some created Poisson structure. And moment map could be derived explicitly in the lab. So again, now this is element here. So exterior algebra, second degree. So this is elements of your algebra functions and elements in G star. And in general, this moment map, I think it was constructed by Krutov and Steinberg that for such Poisson structures given by the bilinear form, you can construct it very easily. So you take a EI will be basis of G, Fi will be the corresponding dual basis in G star, Vj will be basis in your vector module, and G star corresponding dual basis with respect to B, and this is the form. So this is all review of what is going on. Let's speak now about the generalizations of our Poisson story. So we'll start with the quasi-Poisson manifolds, as was defined by Alexey Manin and Schwarber. So it's some generalization of Poisson manifold, homogeneous Poisson manifold. So we start with some Lie algebras that admits non-degenerate invariant symmetric bilinear forms that we will denote by these guys, and let EI and Fi will be the basis of G, and Fi will be the corresponding dual basis with respect to this form. Then we can construct the corresponding Cartan pretensor. So it's some invariant element in the third degree of our exterior algebra given by this formula. So you see that it really fills your form because Fi is a dual basis with respect to your bilinear form. And of course, it will give you the corresponding invariant in the third degree. It will give you corresponding invariant bi-invariant form, free form on your Lie group. So famous Cartan form. Next, we have a Lie algebra homomorphism which defines our infinitesimal action. So you have element of your Lie algebra and you associate the corresponding vector fields that give you infinitesimal action of our Lie group G. That could be extended to a covariant map between exterior algebra of G and exterior algebra of vector fields. So some polyvector fields. What is more important, it's algebra map and it's preserved Schouten brackets. Then a quasi-Poisson manifold is a following gadget. It's a manifold with invariant by vectors that I will denote. Define such that its Schouten bracket is not zero, but we still have a good control of it. So it's image of our Cartan pretensor under this homomorphism. So I will show you in examples how it looks like. So it doesn't define the Poisson bracket anymore. Well, this Poisson bracket will not satisfy Jacobian identity because this guy is vanishing. But still, it's a nice object to study. And it's reasonably recent. Got it. What is that? There is an analog of moment maps for them. Unfortunately, you cannot get a moment map back to your dual of Lie algebra, but you can construct a moment map for such guys with values in the corresponding Lie group. How to do that? First, I will need some additional notation. Let these guys will correspond to left and right invariant vector fields that associated to the element of my Lie algebra G. So how to do it? You know that X is a tangent vector to identity, and then left invariant or right invariant you get by right or left translations. Or you use these formulas the same. Then let EI be a basis of G, and I will need right and left corresponding dual Mauer Cartan forms. So this map, this forms dual to these vector fields. Then the moment map has the following condition. So now it's map that is invariant with respect to a joint action of G. But as I promised, it's a map from manifold to G, not to G star, not to dual of the algebra, but to group. That should satisfy the following condition. And it's you associate it to some quasi-Poisson manifold, not a Poisson manifold. Again, it's a recipe. Somehow you hook almost your version of infinitesimal vector fields corrected by this term that depends on phi. No, go back. And again, here you cook using your moment maps and one form, and you insert it in your now quasi-Poisson structure. So recall that this y star will be mapped from the one forms on your group to one forms on your measure. So with some generalization, there is several equivalent formulations. Probably this one is easier to show in a short talk. I will give you an example of such thing immediately. So the first very simple example is, let's take as a manifold our Lie group G itself. And the corresponding bivector will be given by these wedges. So I will take a right and left vector invariant vector fields. And then one could calculate the Schouten bracket fit, and you will see that will be exactly this third degree invariant form of your group, which is by the same money as the image of your file. Therefore, this is a quasi-Poisson manifold. And the moment map, you can find it. It will be very easy. Here, it's just identity. So quite nice. Let's go further. Let's return to our simple examples. No, before I want to discuss the following thing. In general, could you go back, please? Of course, you know that this probably have very little with a classical moment map because, well, you started with something which is not Poisson, and this identity, how to obtain it, it has values in the not in the group of Lie algebra, but in the group itself. But in fact, sometimes you can integrate your moment maps, the classical moment map, to a group value map by the following recipe. Next slide, which is a bit involved in the definitions. So it was suggested by Alexeyev, Kosmich, and Malekin, based on the dynamical error matrix that was studied effectively by Andrey Krutov and Barchenko. And today we will have a lot of error matrices of different kinds. So this is the first part. So what is this dynamical error matrix? How to construct it? So assume that we have some classical moment map and some Poisson homogeneous thing. Let us start with some meromorphic functions that define in this manner. More important is have this Taylor example. Then we can consider the bivector on my Lie algebra itself, which is given by the following form. So this is the components, EI, ED is my basis. And the components is given by, so I take the adjoint action of some element X, and then I plug it in this formula. Well, what I really do, I plug it in this form of our series. And because I will keep under the carpet some convergences, but it will be some nice function on my Lie algebra. So, and I think Goff and Barchenko showed that this is a solution for so-called dynamical Yang-Baxter equation. I will not show it to you because I decided it would be too much exposition, but it has some nice applications, not only in representation theory, but physics. So then, using this data, I could cook from my Poisson manifold a quasi-Poisson manifold by the following recipe. So, using my moment map, I'm mapping this bivector on my Lie algebra to a bivector on my manifold. I will denote it aerodynamical of mu. So dynamical error matrix map to mu, map by mu. Then Alexeyev, Kosmich, Schwarzberg, and Malekin prove that if you will correct your Poisson structure by this dynamical error matrix, it will become quasi-Poisson. Moreover, if you have your moment map mu, then you can obtain for this quasi-Poisson structure group valued moment map by taking the exponent. So now it's important that we have this non-degenerate symmetric bilinear form on G because we identify G star is G, and then in G, you know that exponent has a nice behavior. I will put under the carpets when it converges. It works in the most cases. So let's see how this some quite heavy machinery will work for our simple SL2 examples. It's easy to calculate with give you to your undergrads that the Cartan free tensor for SL2 will be given by exactly this formula when bilinear form was fixed on the one of the previous slides. Let us look for a fundamental representation. So two-dimensional. Recall that it was our vector fields that gave us infinitesimal action of our group. So to obtain the image of this Cartan free tensor on our manifold, what we should do? Well, we should plug in instead of EHF the corresponding vector fields. You compute and wow, it's 0. So you see that your Poisson manifold becomes also a quasi-Poisson because you had a Poisson structure that's counting bracket is 0. But you know that 0 is equal also to the image of Cartan. Cartan free tensor. Nice. You can also compute this dynamical error matrix. The computation is a bit more involved, but you will get surprisingly 0 again. So you have a quasi-Poisson manifold with no change of your bivector. It's a Poisson and quasi-Poisson, and you can get the group valued moment map by just taking exponent. And surprisingly, when you take this exponent, it will terminate on the second step. So you have identity, something of degree 1. This will you can recognize some elements of your of moment map that was presented before. And when you will take next integration in your exponent, it will be 0. This is basically by some representation theoretic arguments, but you can also compute it precisely. Perfect. Let's see what is going on for our second example, which was contains a joint representation, and it was a supermanifold. So again, I will recall our Cartan free tensor. Then we have our vector fields. We plugged in, and voila, it's 0 again. So I can play in the same game. Moreover, I could compute my dynamical error matrix at 0. And yeah, this is again quasi-Poisson, and I have the corresponding group valued moment map. This exponent is much more tame. Well, you're acting now in stereo algebra. So any exponent will terminate when you reach the dimension. Dimension of this gate is free, so there is no analysis. Let's see what is going on, because it's not regularly the case. Let's make some analysis where this image of free Cartan tensor belongs to. So we know that, as I said, we should just plug in our vector fields. Our vector fields are linear with linear coefficients. So for all the given modules, it will be elements here. No, it's a beautiful piece. So it will be even elements here or here. And we know that it also should be invariant. So hence, if space of homomorphisms, G homomorphisms between third exterior and third symmetric power is 0, then image of a Cartan free tensor is 0. That means that for this particular module, every Poisson structure will be also a quasi-Poisson. In general, it will be not the case. If this condition doesn't satisfy, you can have something perfect. And well, I see already this condition. Such simple models was classified by Zitznagel, it's a student of Arkady Einstein, in the following context. He was studying, press next. He was studying Poisson structures on these symmetric and exterior algebras given by the classical error matrices that was classified by Ilan Greenfield. And also, it was a story about quantum symmetric and exterior algebras that surprisingly appears in the study of these quantum reducible Klein manifolds that Prague non-commutative geometers qualified. So this is exactly quantization of the local parts of the round complexes for these quantum objects. I will make a comment about SO2 in a second. So we have some very good basis to speak of such nice, remarkable modules where we can use this machinery of integrating our moment maps with the group value moment maps to see what is going on with corresponding bivectors. We also notice that the corresponding dynamical error matrices on this supermanifolds was 0. Unfortunately, there is not a, it's not a general fact, or at least I'm not aware, so you can do some step-by-step analysis. So you have a list of such modules, and miraculously for them, for all of them, and for the moment maps given for a Poisson structure induced by the bilinear form, this thing is 0. So I don't have such a nice explanation here, but here it's a bit more involved. So let's see. Next, I promise some moment maps with values in the Poisson, in the dual Poisson-Lie group that was introduced by Liu and Weinstein around 1990s. So much earlier than the group violet moment maps, but somehow in our consideration, you will see the nice diagram. So how to construct them, how to approach. First, let me recall that the Poisson-Lie group is just a Lie group that also a Poisson manifold with a Poisson structure given by the bivector pi G, such that the multiplication map is a map of Poisson manifolds. So you recall that if you have two Poisson manifolds, the direct product will be Poisson. Then an action of a Poisson-Lie group on a Poisson manifold is called Poisson if the following conditions satisfied. So you have your Poisson B vector on your Poisson manifold M, which is denoted by pi L, L in the corner of then it should satisfy the following conditions. So you take a Lie derivative with respect to infinitesimal action of your Lie group, then it should be equal to the image of the corresponding co-bracket. So the co-bracket is a map from G to the second exterior power of G. Let me recall you that due to Greenfield and Belevin, the all Poisson-Lie groups are classified by the corresponding P bialgebras. So if you look infinitesimally at the identity in your group, then the Poisson bracket will correspond exactly to such map. So it will be mapping to the corresponding bivector. Then what is the dual Poisson-Lie group? So it's some Lie group with certain assumptions. For example, it should have the same. It should have the following Lie algebra. So Lie algebra will be the dual vector space of G, and the bracket there is induced by the co-bracket. So if delta for G is a map in this direction, for dual vector spaces it will be mapped in opposite direction, so it will be exactly as you want. So it will be some bracket, and because it's classified by R matrices, it will be well-defined Lie bracket. I refer to some nice paper by Greenfield, Belevin, and many others. And the moment map with values in this dual Poisson-Lie group is a following map. So it's a map now to this G star, which satisfies the following conditions. So again, I could express at my vector field that gives me infinitesimal action by my Poisson bivector and moment map when this XL is a corresponding Latin invariant form one form on G star, which has this value at identity. So when you speak about the dual group, everything is reversed. If you had a, remember that for your Lie group, at identity, element of your Lie algebra gives you some vector field. But for the dual group, your tangent space will be modeled by the G star. So G will give you one form. One. So the definition again, quite intuitive in the way that, well, it's the same old good way to obtain your vector fields in some nice things. And example, which I will not go into details, I'm sure I'm doing this time. This is addressing action of G on itself, and the moment map is identity. And if you like integrable systems, then you like addressing actions, and also some boundaries. But it will be too much to explain it in this short talk. But I will go back to my simple examples. But before, again, surprisingly, there is a way how to go from group valued maps to the moment maps with values in the dual Poisson-Lie group. It was again in work by Alexey Kossen-Schwarzbach about mining pairs. And the construction is the following. So we start with our Poisson-Lie group, and we have some R matrix. R matrix will be element here. It's a classical matrix that defines your Poisson structure. And you look at the quasi-Poisson manifold, and okay, here should be R of. Could you please? Next slide. Yeah. So please forget about this part. You can now construct some B vector on your Lie algebra by anti-symmetrizing your R matrix. So you take R and you take R in opposite direction, and then you can correct your quasi-Poisson structure by the image of this bivector PR. Then one could show that this structure, this gives you a Poisson structure. Next. Then, okay, so we have now recipe how to go from quasi-Poisson manifolds to Poisson manifolds by correcting them by the R matrices. Now, how to get the corresponding, what will happen with the corresponding group valued moment maps? So, if the Poisson structure on your G is given by the standard F matrix, one of the simplest cases, then you have the following construction of the dual Poisson-Lie group. So, fix a maximal torus in your G and some trace of positive roots. This will give you two barrels of A plus B minus. And that per plus minus will denote the projections from barrels to the torus. Then your dual Poisson-Lie group looks as follows. So that it's elements of this product of barrels and algebras which satisfies the following condition. Then how to get your group, how to get your moment map with values in the G star? Well, you can use Gauss decomposition of your Lie group G, which will decompose it basically in upper triangular barrel, lower triangular barrel in the case of GL, or in general, this is P plus, you will get some decomposition like that. So you can factorize it and define these two maps. And next, so this pair of two maps will give you the corresponding moment map with values in T star. And again, you can check that it satisfies the condition of being a moment map. So let's try to do it in our case. I will give very briefly, we'll say, about our Lie groups. So the standard R matrix for SL2 is very simple, given by the following expression. The corresponding dual Poissonian group looks like this pair of matrices when only A is non-zero. Remember, you should multiply them and get identity. When you project as a maximal torus, so maximal torus tell diagonal events. And yeah, note that this is true. So we have our error matrix, we can anti-symmetrize it and map the corresponding bivector to the bivector of another manifold. Here we're speaking about the case when W is a joint representation. You get the following bivector, then you add it to our bivector given by the by linear form. It will be something Poisson, because this guy was not only Poisson but also quasi-Poisson. So this correction gives us back Poisson. And Gauss decomposition will give us corresponding moment mass is values here. You can do the same for two-dimensional module. The formula is just a bit uglier in the first space. And let us see on this diagram. So this is a bit of summary of the talk, telling you what was going on. So we were starting with some Poisson structure in the classical moment map. Then we was correcting this Poisson structure to have a quasi-Poisson structure by our dynamical error matrices. And we was taking exponents to get group value moment maps. And then we can correct this thing again by the error matrix Poisson by error matrix bivector. It's not straight Poisson. Then the resulting guy is Poisson again, but you have a group moment map in values in G star. What was special about our examples? In our examples, we knew that this part was zero and the dynamical error matrix was also zero. Moreover, it happens by the results of Spitznagle that in the examples that we considered when this was zero, this bivector given by the anti-symmetrization of R matrix was also not just the bivector, but Poisson bivector. So we have two Poisson structures. Our initial one and given by R matrix that was compatible. Some bi-Hamiltonian system. So they talk to each other, meaning that this Hausen bracket is zero. You can take any linear combination and get new Poisson. That brings us to the classification result. As I said, that the particular risk probably is not so interested. You can look at the paper that will be in archive soon, I hope. But the following theorem says that if you have some module, let's say simple over some simple algebra G for simplicity, which satisfies the following conditions. First, it has non-degenerate invariant bilinear form. So you can construct initial Poisson structure on the corresponding linear supermanifold. Second, this space should be zero. What you can do in this case then? Well, everything. So you know that for the same money, your Poisson structure is quasi-Poisson, because for this guy, as we discussed, this image of a Cartan pretensor will vanish. Then by some complicated, well, not so, but some considerations, you can show that the corresponding dynamical error matrices will also vanish on your supermanifold. Moreover, you can integrate everything to group valued moment maps. This exactly follows from the recipes that I presented before. Then these two guys are compatible. So your bivector Poisson structure given by a linear form and Poisson structure given by the corresponding error matrix. And using the Gauss decomposition, you can factorize. The list of such modules is explicit. There is not so many of them. So we discussed two for SL2. Then there is a couple of exceptional examples and two series. Take orthogonal algebra and symplectic. you have a standard representation for them. This will be examples of your models. So for orthogonal algebras, you will have odd modules. So you look as opposed to structure on the exterior algebra. And for symplectic guys, the standard modules will be even modules. So responding symmetry. Let me summarize a bit about the motivation, how it all appeared. So it was a story about different Poisson quantizations of the exterior algebra of SL2. So first is well known as just the classical Clifford algebra. So the relations are here, you just deform by the form. Then it was these quantum exterior algebras that appeared in the study of quantum groups. First, it was constructed by Andrey Krutov, then revisited. The general construction was given by Bernstein and Zvitsnagel, but this is a quantization of this exterior algebra with respect to Poisson B vector given by our classical R matrix. So it's now exterior algebra of this adjoint representation for quantum group. And then we was looking for something with Pavlovanich, something that looks like a convex Clifford algebra for the purpose of constructing of Dirac operators. And we found this nice little algebra that was actually deformation of this guy. And we were studying it, and it turns out that this guy is isomorphic to the classical algebra. You have some horrible formulas that gives this isomorphism. It was a bit surprising because some category theory in the construction of this algebra was involved. And we was wondering why this happened. What is the explanation behind this? Well, it turns out that if you look, so it's definitely deformation of your classical exterior algebra. So you can look at the infinitesimal part. So this infinitesimal part should give you some Poisson B vector. And this Poisson B vector is exactly a result of our all constructions. So it's just this direct sum and they compile. Moreover, what you can do, you can find some change of variables that will map this by vector to just P of B. However, this change of variable will be not invariant with respect to action of SL2. That's why you have different version of a moment maps. And yeah, more. So it leads to some quantization also of a Kaplan calculus, and let me give you some review of where these things appears. So yeah, we can now think about the quantum group as the quantization of the corresponding Poisson dual Poisson Lie group with respect to the standard R matrix that defines it. Then I expect that this will boost some developments in corresponding Q-deform and Clifford and Q-deform Clifford algebras and corresponding Dirac operators, because we now exactly know the list of modules of a quantum group when you can do the same, obtain a nice algebra and work. And this is family rich enough. For example, it covers this reduced for quantum. Yeah, so this Q-deform exterior algebra, this one was this non-commutative geometry business. There is also for SL2 analog of a Q-deform Kaplan calculus that have this very nice Kaplan's magic formula in the context of the quantum groups. And I expect that it will work for the examples stated. And there is also some Q-deform Clifford analysis. This is work in progress with research involved. And yeah, this is again some reminders that it looks like when we study some object over quantum group, for example, exterior algebra of some module, we actually quantizing not just the Poisson manifold, but the corresponding Poisson supermanifold. So when your underlying manifold is just M, but your sheaf of function is, for example, sheaf of differential forms. And it gives you a line how to treat it simultaneously with this formalism. And I think this is all what I wanted to say. Thank you.
Thank you very much. Open formal discussion panel. So if you have any questions, please ask. Maybe I'll start the first question. I'm not expert in this field at all, so just an easy question. How can I find that these two Poisson structures are compatible once you obtain from R matrix and from the
Exactly by this theorem. So they will be definitely compatible. No, in another direction. Or we can probably
you mean this
yeah, you need this condition. Or probably we can
maybe
make a step back. So what means that it will be compatible? So means that they something should match. Then you can deduce that. Well, you know that this expression satisfies this condition, right? So if you know that your dynamical R matrix vanishes,
okay.
and your this guy is also Poisson, that it will be automatic. By the I could just write a formula. So you know,
Yes.
you know that this is equal to 0, right? By this result, in assumption that the dynamical R matrix vanishes,
Yes.
and you just
I see.
this.
Just pick from this.
You have a cross term, but actually, depending on the parity, you can switch it.
I see.
Now, if you know that if your original Poisson vector was, if your vector was Poisson, this is 0. If your R matrix give you also Poisson structure, this is 0, and you will get to. But we know that this happened exactly when this home space.
I see.
And this implies, well, with some computations that
Okay.
work in this. There is also, so this is story for simple objects. For direct sums, it will be another story because it requires some fusion involved.
Okay, when we look at this L equivalent to EM by 2 to 4. You had this in examples.
Yeah, I think
Yeah.
I think it's I don't have a formal proof, but I think it should have. Because okay, I almost have a formal proof because so in this quantum Clifford analysis, we was looking at one of the families of Clifford algebras. So with some, it's basically you have a orthogonal algebra in V, and you look at for quantized dispersion. And we was managed to prove that the Clifford algebra, which corresponds to this vector, is isomorphic to the classical one, which means that that is. Show it in paper, but I don't have it yet. It's not conceptual.
Okay, any other question?
So sometimes you know get so I work more on the email I was wondering if you also consider possibly by algebras sometimes.
It's somehow built in this story about quantum. You know, this construction is at least but probably what should so that's a question more or less not for these examples, but for what happens when this condition doesn't diagnose it. Then it will be some truly plausible some story, and then how to quantize it, express it.
Yeah.
New direction. So this thing describes the simplest.
How rare is conditional super? For example, if you consider the space of quasi-Poisson structures, how rare Poisson structures are there?
Quite rare. So I could give you list explicitly. So give me a second. It will be for SL. It will be so SLV. Examples will be V and V star. They're not dimensional. You will have O, and it will be again. Third, you will have SP and DV, and plus several exceptional, well, some points, isolated points, but this is the main factors. For example, for SL2, it will be the corresponding two-dimensional and the adjoint representation, and that's all. So, from one point of view, they're quite rare and special. But they also geometrically they correspond to this flag manifolds with at the same point as this Hermitian symmetrics. So this is another characterization of this list. You just pretend by looking.
If there's no other question, let me speak. Let me thank the speaker again. Pushing more thoroughly later on, and for the discussion, the informal panel. Feel free to ask this nice guy.